Okay, in this clip, we're continuing with the time value of money, the 6 basic concepts or functions of time value of money. And in this clip, we'll start out with sinking fund factor, go into present value of an annuity, and conclude with the mortgage constant. So should be a pretty quick clip here. But the first one here is sinking fund factor, and the sinking fund factor is kind of the Ringo Starr or the drummer. It kind of gets overlooked. Present value and future value get all the attention, and the mortgage constant is pretty important also. But let's not forget about the sinking fund factor. It can be very useful. And the sinking fund factor, it tells you how much you need to save each period in order to accumulate some future amount in time. So it's how much you need to save each year or each month, okay, the same dollar amount to accumulate X at some point in the future. And normally what we're doing, you think of making deposits at the end of a period. Kind of like a Christmas account. A Christmas account is a form of a sinking fund account. And with a Christmas account, what you're doing is you're starting to save a little bit of money at the end of each month. So you'll have a significant amount of money at the end of the year to buy Christmas presents. A sinking fund can also occur, the deposits can occur at the beginning of the period, just like we have annuities do in ordinary annuities. But for this part of the section, for sinking fund factors, we'll just think of a sinking fund occurring, the deposits occurring at the end of each period. There'll be a couple problems in the problem sets where we might have to deal with deposits occurring at the beginning of the period, but we'll worry about that later. The example here, sinking fund factors are very useful in several areas of real estate. One, if we're saving money to replace items on the property. There are several short-lived components of properties. The roof needs to be replaced periodically, carpeting, maybe some appliances. And what we can do is we can figure out how much we'll need to replace an item like the roof, how long it will take, or how long the roof will last. And instead of having one large expenditure at some time in the future, what we can do is we can save a little bit each year or each month, so we'll have enough money to replace the roof when it comes due to replace. In this example, what we're doing is we're saving for a down payment for a house. So we calculate we're going to need $10,000 and in 4 years to buy a house for a down payment. And what we're going to do is we're going to make equal deposits at the end of each year. And we want to put away enough money into this account that's earning 10% interest per year to have exactly $10,000 at the end of 4 years. That's a very good example of a sinking fund. The formula for a sinking fund factor is here. So it's I divided by 1 plus I to the nth power minus 1. So for our example, using our good old 10% interest rate, interest account, and this time a 4-year period, the sinking fund factor is 0.21547. So if we multiply the sinking fund factor times the future amount, the amount we're trying to save or accumulate, in this equation, I'm not sure what P means, but it doesn't mean present value. I think it refers to the $10,000 down payment, but be careful with that. But we're taking the amount we want to accumulate, the future value of a lump sum, times the sinking fund factor, and that will give us the annuity, the amount of money we have to save at the end of each period to acquire exactly $10,000. And here's a check on it, on the calculation. We start out with 0 in our account, and at the end of the first year we're going to deposit $2,154.70. So at the end of the first year we have $2,154.70 because we just deposited it. The second year we're going to earn interest, 10% interest on our $2,154.70, and also make a deposit of $2,154.70. So adding our interest plus our deposit and our beginning balance gives us $4,524.87. That becomes our beginning balance for the next period for year 3. So we start out with a balance of $4,524.87. 10% interest on that is $4,452.49. We're going to make a third deposit of $2,154.70, and that equals $7,132.06. And then for the final, the fourth year, and what we should be approaching here is $10,000 at the end of the fourth year. We have a starting balance of $7,132.06. 10% interest, or 10% of that, is $713.21. We're going to add those two together, plus our final payment of $2,154.70, and that equals very close to 10,000, a little bit of rounding there. So we did get to accumulate, or put away or save $10,000 at the end of the fourth year. My question to you, in this account, we had a 10% assumed interest rate. What if the interest rate was zero? What would we have to put away each year to accumulate $10,000 at a zero interest rate? Well, at a zero interest rate, we would have to put away $2,500, just dividing 10,000 by 4. We'd have to make 4 deposits of $2,500 to basically accumulate $10,000 at a zero, no interest, 0% interest rate. But notice, because we were earning interest on our money, we didn't have to put away $2,500 each period. Okay, we only had to put away $2,154.70. And that difference there between our $2,500 at a zero interest rate and $2,154.70 at a 10% interest rate, that's our interest working for us. That's our money accumulating interest. So we don't have to put away or make, make lower payments than $2,500. So that's the sinking fund. Now, the present value of an annuity. Okay, in this case, what we're doing is we have some annuity, and we're trying to calculate the present value, or what that annuity worth is worth in today's dollars. So once again, remember, an annuity. Okay, an annuity is a very specific thing. And once again, we're going to assume a regular or an ordinary annuity with the payments occurring at the end of each period. But an annuity is an equal stream of payments over some period of time. And here's a good basic example of an annuity. Harold is retiring. Okay, so when you try to figure out how much money to save, or there's some investment, well, you'll receive some future cash flows. What is it worth today? That's a present value of an annuity problem. And Harold is retiring and would like to receive $10,000 per year for the next 20 years. If the investment rate is 10%, how much would you have to pay for this annuity? So the value of the annuity is the sum of the present value of each of the annuity payments. So what we're going to do is basically discount each of those payments. Okay, 20 payments of $10,000 per year over 20 years. Discount each one of those back to present value at a 10% discount rate. So we're discounting now. Now, with a present value of an annuity formula, we don't have to discount each of the $10,000 payments back individually. So one way we could think about this problem would be to discount $10,000 back 1 year, $10,000 back 2 years, 3 years, 4 years, so on, 19, 20 years. So we could think of it as 20 individual present value of a lump sum payment problems, or we can simply, because it's an equal payment, an annuity, simply calculate the present value of an annuity. And the present value of an annuity formula is a good one here. Definitely can't write this one with the mouse pen, but it's the annuity times the factor. In the numerator, we have 1 minus 1 divided by 1 plus I to the nth power, and this is all divided by I. So for our example above, with a 20-year N, 20 period N, and a 10% interest rate, we have 1 minus the quantity 1 divided by 1 plus 1 to the 20th power. Okay, that all divided by 0.1. And that factor equals 8.5136, and we simply multiply that times $10,000. And that gives us $85,136. So the answer to our question, how much is an annuity of $10,000 per year for the next 20 years worth in today's dollars, that answer is $85,136. To check this problem on our calculator, again, while I'm setting up the time value of money menu, I'll remind you once again, what you should always think before you do a problem, is my calculator registers cleared? So clear out your calculator registers. Number two, make sure your payments per year is set to 1 payment per year, and also make sure you're in N mode, because this is a ordinary or regular annuity. Whenever you're doing an annuity problem, you have a payment that we're going to enter, but this is the present value of an annuity. What's the annuity worth in today's dollars? So we're going to be calculating a PV, a present value. So I'll put a box there just to remind me what I'm calculating. And then once again, fill in the I, the N, the I, and the annuity amount. The N is 20. The interest rate is 10, good old 10%. In the problem sets, we'll use plenty of other interest rates besides 10%, but 10% is nice and easy. Once again, these are in the same units. 20 is in years, and 10 is per year. The payment, or the annuity, is 10,000. And make sure future is empty, or put a 0 in it if you're not sure. And then input or compute present value, PV, and you should get, it's actually going to come out to a negative $85,135.64. Okay, or should be very close to that. Okay, and that's the present value of an annuity. Our last concept here, we saved a big one for the last one here, but our last time value of money function or concept is the mortgage constant. And again, you'll be doing lots of mortgage payments. Everybody's going to know how to calculate a mortgage payment by the end of this session, and definitely by the end of your class, whatever you're taking. But the mortgage constant is used to calculate mortgage payments. And the mortgage payments occur typically at the end of the period. So because interest can't be charged until it is earned. So you don't pay interest the day you borrow the money. You pay the interest at the end of the first period. Now, mortgages are typically monthly payments, but you'll notice, especially in some of these initial problems, we're going to assume annual payments. And that's just not to confuse the issue starting out here. But there's plenty of problems in the problem sets where we have monthly mortgage payments where we're going to have to make adjustments to make these monthly mortgage payments, these monthly mortgage constant calculations. So here's our first example. A borrower wants to borrow $80,000 to buy a house. The interest rate is good old 10% per year, and the loan calls for annual payments of 25 years. Again, not typical, but let's go with the problem. And do read all problems carefully. And if they're asking for annual payments, you calculate it annually. If they're asking for monthly payments, you calculate it monthly. What is the amount of the annual payment? Now, the formula for the mortgage constant, again, it's a fairly ugly one, but the mortgage constant is an annuity. It's a constant payment every period, every year in this case. You multiply that times the present value of the annuity, or the 80,000, the amount borrowed in this case. And the mortgage constant factor is I divided by 1 minus the quantity 1 divided by 1 plus I to the nth power. Again, considering our terms here, we have a 10% interest rate per year. So I is 10, or 0.1, 1 minus 1 divided by 1 plus 1, and n is 25 for 25 years. That mortgage factor breaks down to 0.1102. And the way you can think of a mortgage constant or a mortgage factor is think of it as a dollar mortgage. If you had a mortgage that was exactly $1, what would your, in this case, annual payment be on that mortgage? Well, it'd be $11, not $11, 11 cents. Okay, so each year for 25 years, you'd pay 11 cents on that dollar mortgage. Well, our mortgage isn't a dollar, and that's the nice thing about calculating factors is that if it works for a dollar, it works for any other amount. Our mortgage amount is $80,000, so if we multiply 80,000 times our mortgage constant factor, that gives us $8,813.45. And that's our annual mortgage payment using the formulas. On the calculators, again, it's a pretty straightforward calculation, but once again, remember, clear your calculator registers, clear all. Okay, go to your time value of money menu. Make sure you're set up on one payment per year, because in this particular mortgage example, it's an annual payment mortgage. Make sure you're set at N mode. And for a mortgage payment, what we're calculating is the payment, is the PMT. And N is going to be 25 for 25 years. I is good old 10%. N and I are in the same units. N is in years. 10% is per year. And before we calculate the actual payment of $8,813.45, what I'd like you to do is just put in a dollar for PV. Pretend we're borrowing a dollar, and let's calculate that factor first before we calculate the actual payment of $8,813. As always, because your calculator is clear, feature value should be empty, or you can put 0 in it just to be safe. And if you hit payment PMT, you should get 0.1102, or very close to it. The only difference should be rounding. And that's going to come out a negative because we entered this as a positive. Okay? But once again, we're not dealing with a dollar mortgage, we're dealing with an $80,000 mortgage. So you can multiply the mortgage constant times 80,000, or you could simply change your calculator, okay, put, instead of 1, now put in 80,000 into your calculator, and then recompute the payment, and this time you should get the $8,813.45. And again, the calculator makes that a negative because we entered the 80,000 as a positive. Okay, and the sign notation makes sense because what we're doing, we're borrowing 80,000. So when you think about signs in these problems, think about money coming into your pocket or money going out of your pocket. And with a mortgage, if we're borrowing money, okay, if we're borrowing money for mortgagors, okay, homeowners, we're going to get $80,000 when we borrow money from the lender, from the bank. So that's a positive. That's money in our pocket. It goes to buy our house right away, but it's technically money in our pocket. And then each month we're agreeing to pay $8,813.45. That's our mortgage payment. That's money going out of our pocket. So it might make sense to input that or have that as a negative number. Okay, well, we did it. We covered the time value of money functions. The next section has to deal with net present value, internal rate of return. However, before we go to the next section, I'm going to jump all the way to problem set number 1 and go over the answers to problem set number 1 with you, because we've covered all the material, all the calculations, all the concepts we needed to know to solve or complete all the problems in problem set number 1. So I'm going to stop this clip and give you time to work on problems in problem set number 1. I'd like you to try them all. And then why don't you start up the second clip and we'll go over the answers, the calculations to each of the problems in problem set number 1. Signing off. Bye-bye.